Last week, it was a quite important lesson. It's about the main part of this heterogeneous phase equilibrium. So what was it? It's about Raoult's law. Under heterogeneous phase equilibrium, we have only one law. It's Raoult's law. You get the main question based on Raoult's law under the heterogeneous phase equilibrium. And definitely you will get a question in your paper. We did some example from the theory. Theory actually, Raoult's law can be expressed in two ways actually. Main way is that one. Vapor pressure of a liquid is given by the product of mole fraction of that component in liquid phase and the saturated vapor pressure of pure liquid. Pa equals Xa into P naught. At the end of that class, I explained another way, an alternative way for Raoult's law. It says that relative vapor pressure lowering of a component is equal to the mole fraction of the other component. Relative vapor pressure lowering is found once you introduce another liquid to the main liquid. In that case, vapor pressure lowering is there, I told you. Right? Since vapor pressure lowering is there, we can consider relative vapor pressure lowering. Relative vapor pressure lowering. So that's equal to the mole fraction of the other component in the liquid phase. When you do questions regarding Raoult's law, I mean heterogeneous phase equilibrium, I told you, mainly we apply two laws here. First law is the Raoult's law. In the case of Raoult's law, you can see vapor pressure in vapor phase and the mole fraction in liquid phase. The other law we apply is Dalton's law of partial pressure. In that particular case, you saw that Dalton's law of partial pressure, then everything in vapor phase. Vapor pressure in vapor phase and mole fraction in vapor phase, everything is in vapor phase. You should see these differences and similarities, then only you can use these two equations properly. Correct? Yes, other than that, yeah. Based on that, we discussed then some questions. Did we go to the past paper question? No, we didn't go to the past paper question. We will discuss past paper question today. But before that, I go to another theory part here. Right? So when I explain those things, I use one word. It is ideal solution. That I think I use that word, ideal solution. So then question is, what is ideal solution? So I compare this with the ideal gases. Ideal gases we learned under unit 4. Unit 4, gaseous state of matter. That's ideal gas. So if I ask gaseous ideal gas, what is your definition? Ideal gas. You can't say ideal gas is the one which doesn't have attraction and all stuff. That's not the definition. Those are the qualities, properties of ideal gas. No attraction, no volume. Volume of the particle is negligible compared to the volume occupied by the gas. Collisions are fully elastic, right? Pressure exerted by only by the collision between particle and wall of the container. Those are the properties, qualities of ideal gas. Then normally we define ideal gas like this. Ideal gas is the one which obeys Avogadro's law, Boyle's law, and Charles' law at any temperature and pressure. That's how we define ideal gas. So same way here, in ideal solution, we define it like this. Any solution which obeys Raoult's law at any temperature. Any solution which obeys Raoult's law at any temperature called ideal solution. Ideal solution is our topic. Then what is ideal solution? Any solution which obeys Raoult's law should be ideal solution. As we discussed in gases, ideal gas is a hypothetical one. We don't have 100% ideal gas in nature. So here also the same thing. We don't have 100% ideal solution. That's a point. We do all these questions based on then one assumption. So what is that assumption? These solutions behave as ideal solution. Like in gases, we have here assumption, right? Then what is the requirement to be ideal solution? Remember, it should obey Raoult's law. That's the main thing. But what's the requirement here? When you get this type of mixture, you find as ideal solution. Let's say A liquid mixed to B liquid to have AB mixture. Sorry, here you have AB mixture. This is where you get AB mixture. Then I consider the attractive forces of these things. When I consider attractive forces, okay, here the attractive force, it should be FAA. F symbols the force between AA liquid particle here. If it is benzene, then attraction between benzene particle, London dispersion force. B attraction FBB. But once you mix it, what happens? New attraction is formed. New attraction is FAB. New attraction is formed between A and B particles. Earlier AA only, BB only, but once you mix it, there is chance to have attraction between A and B liquid particles. Then this AB can be identified as an ideal solution only if these attractive forces are equal. Got it? That's a requirement to be ideal solution. In this pure liquid, you have attraction. In this pure liquid, you have attraction. These two attractions should be equal. The strength of this attraction should be equal, not the type. Strength should be equal. And those should be equal to the attraction between particle in the mixture. So only if this requirement is fulfilled, this solution is identified as an ideal solution. Ideal solution. Okay. Actually, why do we need these things? Is there an importance here? Yes, because fractional distillation concept can be understood mainly based on this one. And why do we need fractional distillation? No, there are so many applications in fractional distillation. Right. So one famous one is the petroleum refinery. Crude oil is a mixture of several hydrocarbons. These hydrocarbons have different boiling points, Using these differences, we take this liquid in different steps. That's what we do. In one step, we take kerosene. You're familiar with that one. In another step, we take diesel. In another step, we take petrol. So what is happening there can be understood based on these concepts actually. So that's why we need these things. Raoult's law, ideal solution. We need those because definitely there is application. Another famous fractional distillation. I have mentioned that several times in the class. What is it? Production of ethanol, alcohol. When you make alcohol, you need a fractional distillation. You need fractional distillation. Then the concepts in fractional distillation can be understood by Raoult's law and this concept, ideal solution. So, then there are so many applications, direct application in this concept we learn in classroom. Okay. Now you understood what ideal solution. Then you understood the requirement to be ideal solution. Attractive forces should be equal. But the thing is this one, if you use two different liquid, definitely the attractions are different. As example, benzene and toluene, both having London dispersion force, but there will be small difference. Because in toluene, there is another CH3 group, surface area is large. In that case, London dispersion force in toluene will be quite strong. So therefore, there is a small difference. That's what I told you. There is no 100% ideal solution. But we can prepare some solution at the laboratory, which is very close to ideal solution. Right? Which is very close to ideal solution. In that case, we consider this requirement. Attractive forces should be approximately equal. But then attractive forces, the strength can be equal if the type is equal. If the both having hydrogen bond, those are very close. If one has hydrogen bond, the other one has London dispersion force, then no, those are different. Therefore, when you select those two liquid to prepare ideal, you have to be careful with that type of attraction. Then ethanol and methanol, that makes you ideal because ethanol has hydrogen bond, methanol has hydrogen bond. But there is a small difference, but we ignore that one. That difference is ignored. We can assume between methanol and ethanol again we have hydrogen bond and the same strength. Next, when you get water and D2O, water H2O, D2O means heavy water, still it is water, heavy water. Then both having hydrogen bond, attractive forces. Then that mixture should be ideal. Next, when you consider what else? Benzene, toluene, as I explained, it can be ideal. We can assume the attractive forces quite equal. What else? Ethyl bromide, methyl bromide, ethyl bromide and ethyl chloride, dipole. So we have same attraction, quite similar attraction. Then that mixture should be very close to ideal solution. So that's how we prepare. When we prepare ideal solution, we have to make sure that the liquids have similar structural formula and finally similar attractive forces. Got it? Then under this ideal section, so does the crude oil behave like ideal? Yes. Yeah, a kind of ideal. Ideal mean, then now it's not 100% ideal, but yeah, very close. Then ideal solution, we will discuss two main type of graphs. That's about vapor pressure composition and boiling point composition. After that, we will discuss non-ideal solution also. Under non-ideal solutions also, we discuss those two type of graphs. Thereafter, we will discuss fractional distillation process in detail. Yeah, that's end of basic. Let's continue this. Right, the topic ideal solution. Right. I hope you got the requirement. Then remember this one, ideal solution. To be ideal solution, then it's a mixture. Mixture mean A and B should be miscible each other. A and B should be miscible each other. If these are immiscible, there is layer separation. Layer separation, then that's the first type, homogeneous phase equilibrium we discussed. In this particular case, two liquids should be miscible. Right. Oh, that's the main requirement. Then I'm going to give you some examples. Where the solution is very close to the ideal behavior. Let's talk about those examples. These concepts quite easy to understand. I mentioned some example. You remember that one? What are the example? First thing you can say, let's take as a liquid, let's take benzene. As B liquid, let's take toluene. Benzene CH3, right here, A, benzene and methyl benzene, toluene. AB mixture will be these things. That's the AB mixture. So what do you expect the attraction between these two? I mean, benzene. Benzene is a nonpolar hydrocarbon. We know it's then London dispersion force. Toluene is also hydrocarbon. We assume it has again nonpolar hydrocarbon. So the attraction is London dispersion force. We can assume the surface area here quite, the size of molecule is quite same. Therefore, London dispersion force, the strength of this attraction is same. Between benzene and toluene also, benzene nonpolar, toluene nonpolar, between these two again, we have London dispersion force. Approximately the attractive forces are quite equal, so it's an ideal solution. Next one, I got water and D2O. Water and D2O, another example. Then here we have H2 and D2. What about the strength of attraction? Hydrogen bond type, hydrogen bond. This one is also hydrogen bond. D mean hydrogen. Hydrogen mean second isotope. This is water D2O. It should be again hydrogen bond. Quite similar attractive forces. Another example, I can take ethyl bromide. ethyl chloride C2H5Cl. These are permanently polar molecule. So you know the attractive force here. It's a dipole-dipole attraction. It's the dipole-dipole attraction. So this is dipole-dipole. This one also dipole-dipole. This is also in between these two again dipole-dipole because those are permanently polar. Understand? So these type of mixtures, the mixture which has two components with the similar structural formulae. In that case, definitely we get ideal solution. Not exactly ideal solution, but a solution close to ideal behavior. Okay. Ideal solution, right? Okay, then start new point. Right, then I'm going to ask you a small question regarding this. When you mix A and B liquid and assume A B mixture is ideal, right? Mixing A and B liquid gives an ideal solution. So during this mixing, what happened to the heat? Energy is released to the environment, or energy is absorbed, or there is no heat exchange. Process is endothermic or exothermic, or there is no heat change. What do you think? When you mix two liquid, which gives the ideal solution, that process will be exothermic or endothermic, or there is no heat change. No, hey, some of you say no change. Some of you say endothermic. Some of you say exothermic, and some of you say exothermic, sometime endothermic. කපටි උත්තරයක් ඒක නේ. It depends on type of component used, right? Right. Then you know this one. I use the word ideal. If I use the word ideal, what's the meaning of that? Then definitely the attractive forces between two particles in pure liquid and the mixture equal. Right. So then it doesn't exist. It's something else. There is no 100% ideal. It's something else. But if I use ideal, you know, if I use ideal gas, then it obeys what? PV equals NRT. We just apply it. That means if it is ideal, if I refer it as ideal gas, that means no attractive force, everything for ideal. But there is no ideal gas. It's a different story. But remember that one. Here I use that word ideal solution. A and B liquids mix together to form AB ideal mixture. During that process, I asked what happened in terms of heat. Heat is released to the surrounding, heat is absorbed from the surrounding, or there is no heat change. That's what I asked. So I use the word ideal. That means the attractive forces are equal. Attractive forces are equal. So it's something like this then. FAA, FBB, and FAB. These attractive forces are now equal because I use the word ideal. Equal attractive forces are there. Then once you mix A and B, you know first what happened? AA attractions are broken. BB attractions are broken. New AB attractions are formed. That's what happened. Okay. Let's say you have, as example, 4A particles in the sample. 4A particles in the sample mean you get 2 AA attractions. 2 AA attractions. Let's say you have 4 BB particles. Then you have 2 BB attractive forces. Then once you go to the mixture, new AB attractive forces are formed. Then how many? There should be 4. There should be new 4 AB attractions. Did you get this point? You have only 4 A particle in this sample I use. That means there are 2 AA attractions. You can assume like that. Here also 4, then BB, BB. In that particular case, 4 A particles and 4 B particle in the mixture. 4, then that's how we have it. So then 4 AB new attractions are there. I told you when you mix it, these attractive forces are broken. AA should be broken. AA should be broken. BB should be broken. BB should be broken. But since the strength of attractive forces are equal, if I supply 200 kilojoule for this, here also I should supply what? 200 kilojoule. Why? The attractive forces are equal because it's ideal. It's ideal, so attractive forces are equal. Remember that one. Once I use the word ideal, it's ideal. Ideal means attractive forces are equal, 100% equal. Then total energy required to break all these attractive forces, then 200, 200, it's 400. You know, bond breaking requires energy. We discussed that one in the energetic. There is bond breaking here. So we have to supply then 400 kilojoule total to break all these attractive forces. Then new bonds are formed, and these bonds, the strength of AB also equal to AA and BB. So what will be then total energy released? During the formation of bond, just remember energy is released. Then what will be the total energy released here? It will be 400. Why? If 100 joule required to break this attraction, one bond, then there will be 100 joule release due to the formation of this one. Why? The strength are same strength, 100% equal, because I use the word ideal. Did you understand that? So therefore, you see, this is plus 200, 200, and this is minus 400. Then plus minus here cancelled out. There is no heat change. There is no net heat change. So remember that one. If you mix two liquid which gives ideal solution, we don't see any heat change, right? So they don't absorb energy from the surrounding. They don't release the heat to the surrounding. That means when you touch that beaker, we mix A and B in the beaker. So when you touch that beaker, you don't see any heat, you don't see any cold, right? So same temperature remains. So then that's the first thing you should understand. So how does AB become 400 minus? Why? Because 200 mean one is 100, one bond is 100 here. Here 200 mean again one bond is 100. Same energy required because same strength is there. Then when you form AB, that released energy, that energy released should be minus 100. Release minus 100. These are plus 100, like. Okay. Since there are four bonds, new four bonds, it's minus 400. Okay, that's the first thing you should understand. Regarding the heat change, there is no heat change if you prepare ideal solution. Next thing is this one. It's about the volume change. Right. So in non-ideal, when I discuss non-ideal, you will understand this clearly, because then only you can compare this. When you mix AB mixture, which gives AB liquids, which gives ideal mixture, when you consider the volume change, there is no volume change. I mean, we get exactly the expected volume. Why? The attractive forces are equal, then interparticle distance is same. If you consider A liquid, let's say this much interparticle distance, B also the same attraction, same strength of attraction. Therefore, you get interparticle distance, same interparticle distance, same interparticle distance. Then in a mixture also, the strength of attraction is equal. You know, if the strength of attraction becomes strong here, the particle get close to each other. Then interparticle distance decreases. If the mixture has then weak attraction, then interparticle distance increases, because attraction is weak, then they separate easily. But if you get same attraction, then the interparticle distance, you know, should be same here. Did you understand that? It should be same. Same interparticle distance should be there. That means if you get 100 milliliter, here again 100 milliliter, they should be exactly 200 milliliter. Why? They keep in same distance. Why? Because the attractive forces are equal. In non-ideal, it's not 200 actually. I'll show you. In some cases, it's greater than 200. In some cases, it is weaker than less than 200. But in ideal solution, since attractive forces are there, I mean, same attractions, then same distance between particles, we get exactly what we expect. So likewise, then you should know volume change and the heat change regarding these ideal mixing ideal solutions. Let's have note for that one. Okay, next I'm going to discuss now one type of graph we can draw for ideal solution. It's easy to understand, but you have to pay 100% attention to me in this particular case. Right. Look at this. We talk about ideal solution. If it is ideal solution, does it obey Raoult's law? If it is ideal solution, does it obey Raoult's law? Yes, of course, it obeys Raoult's law. Then according to Raoult's law, you know, P equals what? P equals P naught into X. P is the vapor pressure. P naught is saturated vapor pressure of pure liquid. X is the mole fraction of the components in the liquid phase. Then I take P to Y axis. I take X to X axis. Then vapor pressure to Y axis. Mole fraction is mole fraction to X axis. Since P naught is constant at constant temperature, the graph should like what? Y equals mx type. Ne? The graph should be something like Y equals mx type because P naught is constant. So then Y equals mx type. Y equals mx type. Then I draw that one for component A like this. Assume this is your mixture you have. This is the ideal mixture, A and B. Vapor pressure of A in the vapor phase PA. Vapor pressure of B in the vapor phase PB. Sorry. Total vapor pressure here, PT. Mole fraction of A in liquid phase, XA. Mole fraction of B in liquid phase, XB. AB. Those are the normal standard symbol we use. Last week we discussed it. Then I'm going to show you how the vapor pressure PA, varies with respect to mole fraction of A in liquid phase. That means XA. How the vapor pressure of PA varies with the mole fraction of A in liquid phase. PA XA. PA equals P naught A times XA. That's how we get it. Then this is vapor pressure of A. That's in ATA. This is mole fraction. I can say just mole fraction or composition. Composition of A in the liquid phase. So since it's Y equals mx type, the variation should be something like this. Y equals mx type. Then composition mole fraction here. This is mole fraction of A. That start from 0. 0 mole fraction, that means there is no A. Then there is no pressure, PA. Then 0, 0. But when the mole fraction of A increases, then 0, then 0, 0.1, 0.2, like that, it increases. So let's say it's 0.5 here. When it increases, when XA increases, PA should increase. Pressure exerted by A should increase when mole fraction of A increases. Right? It increases further and further linearly like this. And XA can come up to the maximum. What is maximum? Maximum is 1 here. XA is 1 here. Okay? XA is 1. So this pressure is quite a special pressure. When XA is 1, the pressure exerted by A is given by this point. That means this point. What is that point? If I mark, do you know it's a special pressure I told you. Do you know that pressure? What is this? When XA equals 1, what is that pressure? Anyone can understand? Yes. When XA equals 1, we know XA equals 1 means there is no B in the system. XA equals 1. Moles of A divided by total mole. That is cancelled out. That means moles of A is equal to total mole. Then only you get XA1. That means a mole of A equal to total mole mean this doesn't have, the system does not have what? The system does not have B. A only. A only mean it's POA. If it is POA, what about the pressure exerted by POA? It should be P dot A. In other words, saturated vapor pressure of POA. So now look at this. When XA is 1, pressure exerted by A should be P naught A. You can do the same thing for B also. You can draw this graph again. It's very similar to B. Composition, x-axis. Can you see it? Yes. This is vapor pressure in ATM. Right? Now this is small fraction of B. Here again, you know, PB equals P naught B times XB. That's the equation when you apply Raoult's law to B. PB equals P naught B times XB. Then the variation is again y equals mx type. Y equals mx type. So I can put it like this. XB increases from 0, then 0.5, and you get 1 here also. But it's okay. PB varies like this. Right? Linearly, y equals mx type like this. As you can see here again, XA equals 1, XB equals 1. XB equals 1 mean moles of B divided by total mole cancelled out. That's why XB is 1. Then moles of B is equal to total mole. That means the whole system has B only. It's the POB system, POB condition. If it is POB, PB will be P naught B. It's a saturated vapor pressure of POB. So this will be then P naught B. Got it? So that should be the variation of vapor pressure of one component with respect to mole fraction of that component in liquid phase. Y equals mx type. When mole fraction is 1, that's the saturated vapor pressure of PO component. Right. I can put it like this. But you know, we don't have to draw these two in two different graphs. I can combine these two graphs together and give just one graph. I can combine these two graphs and give it as a one graph. Why? There is a relationship between XA and XB. Do you remember that relationship? XA plus XB is always equal to what? 1. XA plus XB is equal to 1. Total mole fraction is equal to 1. So based on that relationship, then I can combine these two graphs. That's what I'm going to do now. I'm going to combine these two. Very simple, right? It's not then that much complex one. This is vapor pressure in ATM. This is also vapor pressure in ATM. This axis is composition again. Composition, can you see that? Composition. Composition mean in terms of mole fraction. I put mole fraction XA here and the mole fraction XB here. XB here. XA varies from 0 up to 1. Then what about XB now? If XA is 0, what is XB? XA plus XB should be 1. Then if XA is 0, XB equals 1. Simple. XA plus XB is 1, then XA 0 mean XB is 1. Then XA 0 mean XB 1. Then XA move up to 1. Then if XA is 1, XB should be 0 because addition is 1. It's simple. So this should be now 0. Right. I hope you understood that part. Relationship in mole fraction. Right. Now look at this. Then I'm going to represent how PA varies here. This is variation of PA, vapor pressure of A with respect to mole fraction of A. Then for A, actually the origin is this. XA0 part is the origin. XA0 part is origin, right? Then it varies linearly like this. It varies linearly like this. Can you see that one? Is my graph is this way? Okay. That's the variation of vapor pressure of A, PA, with respect to mole fraction of A. Correct? Then when XA is 1, I told you the vapor pressure is P naught A, saturated vapor pressure of P of A. Okay, that's the story for A. What about the story for B now? You see now, origin for B is when XP is 0. XB is 0, that is the origin for B. Where is XB? XB is 0 here in this side. So therefore for B, the origin is this point. The origin is this point. Now it linearly increases. I mean, XB increases from here to here, from right to left. XB increases from here to here. Then the PB should increase like that. PB also should increase like this. Okay. I draw it something like this. It's a straight line. Okay, I think you can see that one. So this is actually variation of vapor pressure of BPB with respect to XP. If it is exactly then 100% ideal, then these two P naught A and P naught B should be equal. This is now P naught B. When XB equals 1, the pressure is P naught B. If it is 100% then ideal, then these two values should be equal, and this cross mark should be exactly at half mole fraction. But now normally it doesn't happen, right? Normally it doesn't happen. So then according to my example, you see P naught B here, P naught A here. Which one is greater? P naught B is greater. P naught A is smaller than P naught B according to my example. Right? So, but there will be another example where P naught B here, P naught A here. That means P naught A greater than P naught B. That's again possible. That is another possibility we can have. Right? Then there is a line from here to here. I can draw, I can connect these two. If you can connect these two, remember, that is actually the variation of total vapor pressure of the system. That's the variation of PT, PA plus PB. That's the variation of PT, PA plus PB. Okay. If it is 100% pure, then it should be parallel line. By taking these two, we can easily prove this line is total vapor pressure. If you want, I can show how to prove it, but there will not be that type of question. Only then you should understand red line, vapor pressure of A with respect to XA, blue line, vapor pressure of B with respect to mole fraction of B, and black one, total vapor pressure of the system with respect to mole fraction of A or B. Got it? This graph is called vapor pressure composition diagram. No space to write the topic. That is called vapor pressure composition diagram. Shall I write it here? Vapor pressure composition diagram. That's the topic, vapor pressure composition diagram. Okay, let's have the note for this one. Without any, write the topic. Write the topic. Topic is this, vapor pressure composition diagram.